let us now evaluate, given a point O, what would be the angular momentum given angular velocity omega. We again go back to the definition. This is the body, it is rotating about this point with component omega y, omega x and omega z. The angular momentum vector L is given as summation mi Ri for ith particle cross Vi, and we just saw that I can write Vi, which is nothing but dr over dt as omega Ri cross Ri, and therefore the angular momentum vector L is equal to summation I mi Ri cross omega cross Ri. So, this is the general vector L, summation I mi Ri cross omega cross Ri, and this is what I want to evaluate now. Remember now, omega has 3 components. So, let us write omega cross Ri first, which is nothing but omega x in x direction, omega y plus omega z cross xi plus yi plus zi k, and this comes out to be in I direction it will be omega y zi minus omega z yi plus j omega z xi minus omega x zi plus k omega x yi minus omega y xi, and therefore the angular momentum L is going to be equal to summation mi xi I plus yi j plus zi k cross I omega y zi minus omega z yi plus j omega z xi minus omega x zi plus k omega x yi minus omega y xi. For simplicity, let me first take only the x component of L. This will come out to be summation mi. For x component, let us start multiplying. J cross k would give me one component, so that will be yi omega x yi minus omega y xi plus k cross j would give me a component, that will be minus zi omega z xi minus omega x zi. When I collect like terms, you will get omega x yi square plus omega x zi square minus omega y xi yi minus omega z xi zi. So, let us collect these terms and write Lx as summation I mi yi square plus zi square times omega x minus I mi xi yi omega y, and similarly minus summation I mi xi zi omega z. Let me put these terms in brackets and identify them. You recall, this is the perpendicular distance yi square plus zi square of ith particle from the x axis. So, this is nothing but moment of inertia about the x axis. Let me write this as Ixx omega x plus, let me identify this term, minus summation I mi xi yi. Let me define this as product of inertia I xy and multiply by omega y, plus last term I identified as product of inertia as I x z omega z. So, you see relationship between the x component of the angular momentum and different components of angular velocity is slightly more involved. You can similarly do calculations for other components, and I will leave it for you to work out, so that you will find that Lx, which we just evaluated, is Ixx omega x plus I xy omega y plus I xz omega z. Similarly, you will find Ly would come out to be I yx omega x plus I yy omega y plus I yz omega z, where Iyx is again a product of inertia involving mi, yi and xi. This is moment of inertia about the y axis, and this is product of inertia involving y and z, and Lz similarly would be I zx omega x plus I zy omega y plus I zz omega z, where Izz is the moment of inertia about the z axis, Izy and Izx are products of inertia. Let me define them. Ixy is going to be equal to Iyx, which is equal to minus summation mi xi yi. Ixz is going to be equal to Izx, which is equal to minus summation mi xi zi, and Iyz is going to be equal to Izy, which is equal to minus summation mi yi zi. In general, this relationship can be written as a matrix multiplication as vector Lx, Ly, Lz, three components are equal to I xx, I xy, I xz, I yx, I yy, I yz, and I zx, I zy, I zz, a matrix times omega x, omega y, omega z. And this quantity, this matrix, is known as moment of inertia tensor. It is a tensor because it has 9 components which transform in a particular way. So, the situation is quite complicated. To calculate Lx, Ly and Lz, we need these 9 components, well really 6 components, because these components are equal. Zx is equal to this and Zy is equal to Yz. 6 components, multiply by them omega x, omega y and omega z, and calculate the angular momentum. Fortunately for us, there is a simplicity involved. For any rigid body, about any point, there exists a set of axes known as the principal set of axes, so that the off diagonal elements I x y, I y x is 0, I x z, I z x is 0, and I y z, I z y is equal to 0, and therefore, L vector simply becomes equal to I x x omega x I plus I y y omega y j plus I z z omega z k. For any rigid body at any point, I can find a set of axes which are obviously oriented in a certain way about the body. So, they are very specific to the body and attached to the body, so that the off diagonal elements of the moment of inertia tensor are 0, and L assumes a very simple form like this. So, therefore, I can write by taking components along the principal set of axes as I x x omega x in I direction, I y y omega y in j direction plus I z z omega z in k direction.